I want you to just picture something for a second. What happens when a single tiny microchip inside a massive 10,000 server data center gets, say, 3 degrees too hot?
Just 3 degrees.
Right, just 3 degrees. I mean, if it's your laptop at home, maybe a fan spins up, it gets a little loud. But at the hyperscale level, if you don't catch that specific 3-degree variance in, like, exactly 60 seconds.
You're not just dealing with a melted piece of silicon at that point.
Exactly. You are looking at a full-blown, cascading thermal runaway, like an event that can take an entire regional network completely offline.
Which means freezing financial transactions, dropping, thousands of video calls simultaneously.
And costing millions of dollars a minute. It's wild to even think about.
Yeah.
But today, we actually have our hands on the literal playbook for how you stop that exact nightmare scenario. Welcome to the deep dive, by the way.
Thanks. Yeah, it really is a terrifying level of responsibility when you stop and think about it. And yet it's happening every single second of every day.
Which is crazy. So for this deep dive, we are looking at the SuperCloud Composer, or the SEC. Specifically, their Monitoring Details User Guide, Release 3.12.0 from April 2026.
Right. And, user guide sounds like one of those flimsy booklets you just toss in a junk drawer after you buy a microwave or something.
Totally.
But this document is something entirely different. It's basically a window into the absolute, almost godlike visibility that's required to keep modern digital infrastructure from just tearing itself apart.
Yeah, and I really want to focus on that word, visibility. Because listening to this right now, you probably interact with these massive data centers every single day without ever giving them a second thought.
Most people do.
Right. Like when you stream a movie or query a huge database at work, you just expect it to work. But this manual, it really proves that keeping things just working requires tracking thousands of disparate metrics all at the same time.
Oh, easily thousands.
We're talking raw I/O bandwidth, memory state percentages, and the exact Celsius temperature of the air being sucked into one very specific drawer in a giant rack of servers.
It gets incredibly granular.
It does. So our mission today is to decode not just what data the system actually collects, but the underlying mechanisms. Like why tracking these specific data points is literally the only way these facilities survive.
And I think the most immediate hurdle to that survival isn't even the hardware failing. It's actually the human operator's inability to comprehend the sheer scale of the telemetry.
Oh, the cognitive overload.
Exactly. I mean, if an administrator's monitoring 5,000 servers and each server is spitting out 100 data points a second, the human brain just shuts down.
Right. It's just a wall of noise.
The noise completely drowns out the signal.
Yeah.
So before we even look at a single CPU metric, we really have to examine the lens that the SEC uses to filter all that noise.
Which is why the manual opens right up with this deeply robust analytics engine interface. It's sitting on top of this massive index database, just chewing on historical data and predictive analytics.
Yeah, it's a very powerful setup.
But the feature that immediately stopped me in my tracks was something they call quadrant magnification. It addresses that exact cognitive overload you just mentioned.
Oh, the quadrant magnification is just a masterclass in UX design for high-stress environments.
Right.
The manual actually notes that you just move your mouse over a specific quadrant on the screen, and you simply use the mouse wheel to zoom in and out.
Right.
And as you do, the histogram flattens out.
I kept visualizing this like using a digital microscope on a living organism. Let's play out a scenario here. Say it's 3:00 a.m. An alarm goes off.
The worst time for an alarm.
Always. You pull up the SEC dashboard and you see this massive, terrifying vertical red spike on a network traffic chart. Now, a static image of that spike is essentially useless, right?
Right. It just tells you something broke.
Right. It doesn't tell you the sequence of events at all.
And a static spike induces panic. And panic leads to reactionary, usually incorrect troubleshooting. But with this magnification feature, you put your cursor right on that spike and you scroll.
You're literally stretching time.
Yes. You take that massive vertical wall of data and you just flatten it out across your monitor. Suddenly, you aren't looking at some vague outage at 3 a.m. You're looking at 3.0 in 12 seconds, then 3.00 at 13 seconds.
And 3.000 in 14 seconds. You're isolating the exact millisecond the whole system went rogue.
And that level of granular isolation completely changes your entire diagnostic approach.
Yeah.
You might see that at exactly 14 seconds, a specific storage drawer spiked in latency.
Okay, yeah.
And then at 15 seconds, the CPU spiked to 100% because it was trying to wait for that storage. And then at 16 seconds, the network port just dropped all its packets.
So the magnification actually gives you causality.
Exactly. It gives you the story.
And to help define those temporal boundaries even further, the SCC integrates this bait picker tool. And it's not just like clicking a day on a static calendar.
Yeah.
You're slicing the telemetry by start date, end date, and exact time down to the literal second.
Right. You lock in the exact window of the crime, basically.
Yeah. And once you found the anomaly in that flattened histogram, the manual points out the report drill downs feature.
Which is signaled by the cursor changing to a hand symbol.
Right.
It seems like such a minor detail, but again, in a crisis, removing friction is everything.
I completely agree. So you're staring at this high-level quadrant, you see the storage latency spike we just talked about, your cursor turns into a little hand, and click!
And you're in.
You completely bypass like 5 layers of clunky navigation menus and drop directly into the itemized granular report for that specific piece of hardware. You go from the orbital view all the way down to the street view instantly.
It's brilliant. However, this entire flawless investigative process assumes one critical thing.
What's that?
That the data you are actually looking at is true.
Oh, yes. This brings up my absolute favorite part of the first section in the manual, the error icon. The broken cloud.
It's so jarring to see.
It is. The manual literally shows an icon of a cloud split in half with the text, "Oops, something went wrong." When I saw that in a highly technical server management guide, I actually laughed out loud.
Yeah, it feels out of place, but it addresses the classic watcher's dilemma, right?
Yep.
What monitors the monitor?
Exactly.
The manual is very, very specific about when this broken cloud actually appears. It's not telling you a server is broken. It is telling you that the SCC itself has lost the ability to verify the data.
Right. The manual specifically cites API errors, so HTTP 4XX and 5XX codes or incorrect response data formats. And I want to unpack that because throwing an HTTP error in a management dashboard means something very specific is happening on the back end.
Let's definitely draw the distinction between those two error families, because it matters. If the SEC throws a 5MX error, like a 503 service unavailable or a 500 internal server error, the dashboard is essentially saying the telemetry gathering service on our end has completely crashed.
Or it's just too overwhelmed to process the data coming from the servers.
Exactly. The SEC's own backend is failing.
But a 4MAC-X error, like a 400 bad request, that means the client, maybe the actual web browser the administrator is using, asked the database for a temporal slice of telemetry in a format the database just didn't understand.
Or maybe the authentication token expired, which would result in a 401 unauthorized.
Right.
And then there's the incorrect response data format, which is perhaps the most insidious one.
How so?
Well, imagine the server is supposed to send its temperature as an integer, say the number 35, but due to some weird firmware bug, it suddenly starts sending the string value, the actual words 35.
Oh.
The SEC database just rejects it. It doesn't compute.
So the chart just goes completely blank.
And that right there is why the broken cloud icon is so vital. If an admin is looking at a CPU utilization chart and the line suddenly drops to 0 and stays blank, the natural assumption is just that the server powered off.
Which means they might just casually reboot it or maybe even ignore it for a while.
Right. But if they see that blank chart accompanied by the broken cloud icon, the narrative shifts entirely. The server might not be off.
It could be on fire.
Literally. It might be running a critical database at 110% capacity, melting the motherboard, but the telemetry feed, the actual API, reporting that heat has just formatted its payload incorrectly.
Wow.
The broken cloud tells the admin, do not trust the silence.
Do not trust the silence. That is a brilliant failsafe. So, okay, assuming our lens is clean and our API calls are returning beautifully formatted JSON data, we need to know what we're actually looking at. We really have to map the territory.
We need to transition from the software abstraction down to the macro architecture of the physical hardware on the data center floor.
Right, so the manual organizes this physical map into 2 main areas, a tree view and a navigation view. And the absolute highest level in this hierarchy is the POD. POD.
In the Supermicro ecosystem, a POD is defined as a physical collection of multiple racks and their associated objects. It's the macro building block.
Let's visualize that for the listener. A data center might be a massive warehouse, but you don't just plug 10,000 servers into a single wall outlet. You group them.
Naturally.
So a POD is like a dedicated row or maybe a secure caged area containing a dozen massive steel racks, all sharing dedicated power distribution and top-of-rack switches.
And then moving down the tree, Within that POD, you have groups.
Right.
A group is a logical or physical collection of one or more racks. And then finally, beneath that, you have the rack itself, the actual physical 42U or 48U metal cabinet that's bolted to the concrete floor.
Got it. And to give the human operator a fast pulse on this whole hierarchy, the SEC uses a carousel view.
Yes, the carousel view is key.
It provides this rapid-fire dashboard of current health, so good, warning, critical, and an inventory of current resources. Now, this inventory list is incredibly dense. It lists systems, switches, JBO storage, JBOD, and then it just casually lists NVMe over TCP.
That is a detail we absolutely must pause on,
I was hoping you'd say that.
because NVMe over TCP is fundamentally changing how modern data centers operate.
Okay, so my understanding of NVMe non-volatile memory express is that it's incredibly fast flash storage that usually plugs directly into the PCI slots right on a motherboard.
Correct.
It's fast because it's practically sitting right next to the CPU. But over TCP means it's running over a standard Ethernet network. Doesn't that just defeat the purpose? Doesn't the network add massive latency?
10 years ago, yes, absolutely. Putting storage traffic over standard TCP/IP was considered a huge bottleneck. You'd use dedicated fiber channel networks or just accept the latency of standard ISCSI.
Right.
But NVMe over TCP encapsulates those extremely lightweight NVMe commands directly into standard TCP/IP Ethernet frames. And with modern switches pushing 100 or even 400 gigabits per second, the network is simply no longer the bottleneck.
Wait, really? So you're telling me a CPU in rack A can reach all the way across the data center floor over a standard Ethernet cable and read a flash drive in rack D? And it happens so fast the CPU essentially thinks the drive is plugged directly into its own motherboard.
That is the exact magic trick.
That's wild.
And the fact that the SEC carousel view monitors this specific protocol is our first major clue about the true nature of this hardware. It tells us we aren't dealing with static servers anymore. We are dealing with composable infrastructure.
Composable infrastructure,
Yeah.
which leads perfectly into the most fascinating part of the carousel view, the composed nodes. The manual lists the states these nodes can be in as allocating, allocated, assembling, assembled, and failed.
Right.
When I first read assembling, I genuinely tried to picture digital Lego blocks building themselves in real time, but it's far more complex than that, isn't it?
The Lego analogy is super common, but I actually prefer to think of a composable infrastructure like a high-end, highly automated restaurant kitchen.
Okay, I like that. Let's build the kitchen. How does that work?
Well, in a traditional data center, you buy a server. It comes with a fixed amount of CPU, a fixed amount of RAM, and fixed storage physically bolted inside that one metal chassis.
Okay,
That is a food truck.
a food truck, got it.
The cook, the prep table, and the fridge are all jammed into one tiny box. If you suddenly get an order for a massive, complex banquet, say, a huge machine learning workload,
Yeah.
the food truck just fails. It simply doesn't have enough prep tables.
And you can't just magically make the physical food truck bigger. You are completely stuck with its physical limits.
Exactly. But a composable infrastructure decouples all those components. Imagine a massive kitchen where the chefs and the CPUs are in one room, the prep tables, the memory are in another room entirely.
Okay.
And the ingredients, the storage, like those NVMe drives we just discussed, are housed in a massive warehouse. The SuperCloud Composer is the head chef, the expediter.
So if a user submits a workload that requires insane amounts of fast storage but very little CPU power, the SEC doesn't just go look for a pre-built server that happens to match that. It builds a custom one.
Through software, yes. It reaches out over that incredibly fast NVMe over TCP fabric and logically wires those disparate physical components together. It dynamically creates a custom server on the fly.
So when we look at those states in the manual allocating versus assembling, we're actually watching the head chef operate in real time.
Precisely. Allocating means the software has received the order and is checking the inventory. It's reserving the CPUs in rack 1, reserving the NVMe drives in rack 4, and claiming the necessary network bandwidth. It's locking down the resources so absolutely no other process can touch them.
Then what actually happens in the assembling state?
Assembling is the physical reality catching up to the software request. The SEC is actively sending instructions to the PCIe switches and the network fabric managers, telling them to alter their routing tables.
Wow.
It is carving out the secure, isolated pathways so that CPU in rack 1 can securely talk to the storage in rack 4.
It is physically weaving the digital fabric together.
And tracking these specific states is vital for diagnostics. If a node gets stuck in assembling and then drops to failed, the administrator knows immediately that it isn't a lack of inventory. The parts exist.
Right, because it passed the allocating phase.
Exactly. The failure occurred in the fabric manager's ability to create the logical connection. Perhaps a top-of-rack switch is just out of available routing table entries?
It completely shifts the entire paradigm of IT management. You aren't fixing individual static servers anymore. You are managing the fluid dynamics of raw compute materials.
Fluid dynamics is a great way to put it.
And once that custom node is assembled and the actual application starts running, we have to measure how well those raw materials are performing.
Which naturally brings us to system performance metrics. The pulse of our newly assembled machine. The manual outlines 3 critical averages: I/O bandwidth, memory bandwidth, and processor bandwidth.
Let's start with I/O, or input-output bandwidth. The manual measures this in gigabytes per second and notes it is based on PCIe and DMI data transmission rates. Now, I am familiar with PCIe, Peripheral Component Interconnect Express.
Right.
That's the main superhighway on the motherboard where the CPU talks to the graphics cards or the super fast network adapters. But what is DMI? Why is that specifically called out in the manual?
DMI stands for Direct Media Interface, while PCIe is the highway for the high-speed, heavy-lifting components. The DMI is the dedicated link between the CPU and the platform controller hub, or the PCH.
Okay, and the PCH handles all the slower everyday traffic, right? Things like USB ports, SATA drives, the system clock.
Exactly. And the reason the SCC monitors both is because a bottleneck in either can totally cripple a server, but in entirely different ways.
So.
You could have a machine learning workload pushing massive amounts of data through the PCIe lanes to the GPUs, and everything looks totally fine. But if your DMI link gets saturated because, say, a backup script is aggressively hammering an array of slow SATA drives attached to the PCH,
Oh, I see.
the CPU suddenly can't even process basic system interrupts. The whole machine just stutters and hangs.
So by monitoring both PCIe and DMI transmission rates, the SEC ensures you aren't just looking at the flashy sports cars on the highway, you are also making sure the local delivery trucks aren't blocking the main intersection in town.
That's a great way to visualize it. Now look at the second metric, average of memory bandwidth. The manual specifies this is measured as a percentage, and it is the memory utilization across all available memory channels.
Right.
It explicitly says this is an aggregate of all memory controllers on all processor sockets.
I noticed that. Both the memory and the processor bandwidth metrics heavily emphasize that they are aggregated across all sockets. Why the insistence on aggregation? Why not just look at them individually?
It addresses a massive physical reality of modern server architecture called NUMA. It stands for non-uniform memory access. Modern servers don't just have one CPU anymore. They usually have 2, sometimes 4, or even 8 massive processors on a single board.
Right, they're huge.
And each of those processors has its own dedicated banks of memory physically wired closest to it.
Oh, I see. So if CPU 1 needs data that is currently stored in the memory banks physically wired to CPU 2, it has to literally reach across the motherboard bus to get it, which adds latency.
Exactly. That cross-socket traffic is very expensive from a performance standpoint. If an administrator is looking at a fragmented dashboard, they might see that the server has, say, 50% of its total memory free.
Sounds healthy.
Right. But what if all the memory attached to CPU 1 is 100% full, and the memory on CPU 2 is completely empty?
CPU 1 is going to start thrashing, trying to pull data across that NUA boundary, and the application will crawl to a halt, even though the overall dashboard says 50% free.
Which is exactly why the SCC insists on aggregating utilization across all memory channels. It forces the administrator to look at the holistic pressure on the entire memory subsystem, preventing a false sense of security.
It also strikes me that tracking these 3 specific metrics, I/O, memory, and processor, allows you to spot the actual root cause of a bottleneck, not just the symptom. Let's go back to our high-end kitchen analogy for a second.
Sure.
What does a bottleneck look like through these 3 specific metrics?
Let's say you get an alert that a critical database query is timing out. Users are furious. You open the SCC. The average processor bandwidth your line cooks shows they're only working at 10% capacity. They're basically standing around waiting.
Okay, so the CPU is clearly not the problem.
Right. You look at the I/O bandwidth of DL8s, the waiters bringing ingredients from the warehouse, it's pushing 100 gigabytes a second. The waiters are sprinting.
So the network and the storage are incredibly fast. No problem there.
But then you look at the average memory bandwidth, your prep tables, it is pegged at 99.9%.
The prep tables are completely covered in food.
Yes.
The line cooks have literally nowhere to chop the vegetables. The waiters keep bringing more and more ingredients, but there's no physical space to stage it before cooking. The memory is starved for capacity, which in turn starves the CPU.
The system is perfectly healthy from a compute and storage standpoint, but it is totally bottlenecked by physical memory capacity. Tracking these three variables simultaneously is the only way to diagnose that specific cascade effect.
But pushing those waiters to sprint at 100 gigabytes a second and keeping those line cooks on standby requires massive amounts of physical energy. The digital abstractions we've been talking about suddenly collide head-on with the laws of thermodynamics.
And the laws of thermodynamics are entirely unforgiving.
Mm.
In any hyperscale deployment, compute power is theoretically infinite, but power and cooling are the absolute physical constraints. You cannot cheat them.
The manual breaks this down into power supply metrics and thermal metrics. Let's look at power first. Under power supply, the SCC monitors three distinct values: the sum of capacity watt, the sum of output watt, and the sum of server consumed watt.
Right.
Now, I understand capacity, that's just the maximum rating of your power supplies, and consumed is what the server is actually eating to do its calculations. But why track the output watt? Shouldn't output and consumed be exactly the same thing?
In a perfect universe, yes. But we live in a universe with electrical resistance. You really have to consider the efficiency curve of the data center power supply.
Oh.
A server requires highly conditioned direct current, or DC power, at very specific voltages, usually 12 volts or 5 volts.
Okay.
But the data center delivers massive amounts of alternating current, or AC power, straight from the main grid.
So the power supply has to physically convert the AC wall power into DC server power.
And that conversion process is never 100% efficient. Even with incredibly high-end 80 PLS-US titanium-rated power supplies, there is always a loss. The power supply pulls power from the wall, converts it, and outputs it to the motherboard.
Right.
But during that transit across the copper traces, due to voltage regulators and basic impedance, a small percentage of that output power is lost before the CPU actually consumes it.
And what happens to that lost power? It doesn't just vanish into thin air.
It manifests as heat.
Of course it does. Heat is the enemy.
So tracking the delta between output watt and consumed watt tells an administrator the exact efficiency health of their power delivery system. If that gap starts widening unexpectedly,
It means something is degrading.
yes, it means a voltage regulator is failing, or a power supply component is degrading and generating excess heat, which could literally lead to a localized hardware fire.
Wow. That perfectly transitions into the thermal metrics. The manual explicitly states that the SEC tracks the highest inlet temperature of drawer in Celsius. It doesn't prioritize the CPU core temperature or the exhaust temperature. It focuses specifically, almost obsessively, on the air going into the front of the server.
And that singular metric is the most important leading indicator of a catastrophic facility failure. To understand why, you really have to visualize the airflow of a modern data center. It relies on a principle called cold aisle containment.
Okay, set the scene for me. What does that actually look like physically?
Imagine two long rows of server racks facing each other. Massive industrial air conditioners pump freezing cold air up through perforated tiles in the floor into the space between those two rows. This is the cold aisle. Often, they literally build a physical roof and doors over this aisle to trap the cold air inside.
So the servers sit there, sucking that pressurized cold air into their front inlets, blowing it over the hot CPUs and memory banks, and then exhausting the resulting hot air out the back of the racks into the hot aisle, which is then routed back to the air conditioners to be chilled again.
It is a massive, carefully calibrated respiratory cycle. The pressure in the cold aisle must be perfectly balanced so that the servers don't have to work hard to pull the air in. Now, why monitor the inlet temperature specifically?
Right, why not the CPU?
Because if a CPU gets hot, that is a local hardware issue. The application is running heavy, or maybe a heat sink failed. The server will just throttle itself to survive.
But if the inlet temperature rises...
If the air entering the server is hot, the ambient cooling of the entire physical room has been compromised.
What causes that? Just an air conditioner failing?
That's the obvious cause. But the more insidious cause is a loss of static pressure. Say a technician pulls a dead server out of a rack and forgets to put a metal blanking panel in the empty slot.
Oh no, just leaving a gap.
Just a gap. Suddenly you have a massive hole between the cold aisle and the hot aisle. The freezing pressurized air in the front simply blows right through the hole into the exhaust, completely bypassing the servers.
Which means the servers above and below that hole don't get enough cold air.
Worse, The massive exhaust fans on the other servers create a negative pressure zone, and they start sucking the 40 degrees Celsius exhaust air from the hot aisle backward, through that hole, and right back into the front inlets of the racks.
They're literally breathing their own exhaust.
Exactly. And this triggers the thermal runaway loop we mentioned at the start. The inlet temperature sensor registers the heat. The server's BMC panics and spins its internal cooling fans up to 10,000 RPMs to pull in more air.
But pulling in more air just pulls in more hot exhaust.
And spinning those fans at maximum RPM requires massive amounts of power. Massive power draw generates even more heat inside the chassis. The exhaust gets hotter, which leaks back to the inlet, making the inlet hotter, which spins the fans faster. Within 3 minutes, the silicon reaches its thermal limit of around 105 degrees Celsius, and the hardware simply drops offline to prevent a physical fire.
A cascading failure caused by a single missing piece of sheet metal. It's crazy to wrap your head around.
That is why the highest inlet temperature of drawer is the canary in the coal mine. It doesn't tell you a server is working hard. It tells you the physical environment that sustains the entire data center is collapsing.
Okay, so we've established how critical it is to keep these processors cool and fed with clean power. But all of this compute power, all these assembled nodes and thermal dynamics, they exist for one solitary purpose: to process data.
The ingredients for our kitchen.
Exactly. Which brings us into the deepest levels of the hardware tree in the manual: storage drawers and switches. Let's look at the storage first. The manual differentiates between JBOF and JBOD enclosures.
These are standard industry acronyms that delineate the physical medium of the storage. JDOF stands for just a bunch of flash, and JBOD is just a bunch of disks.
So JBOF is populated entirely with solid-state NVMe drives. No moving parts whatsoever. This is the incredibly fast, high-tier storage we were talking about earlier with NVMe over TCP.
Yes, this is where your active databases, real-time analytics, and hypervisor swap files live. The data that needs to be accessed in microseconds. JDOD, conversely, is populated with traditional spinning magnetic hard disk drives, HDDs.
The massive platters spinning at 7,200 RPMs, they're much slower, but you can pack 20 or 30 terabytes onto a single drive very cheaply. So that's the deep archive: backups, long-term logs, cold storage.
The distinction in monitoring these two types of enclosures lies in the drive states. The SEC tracks whether a drive is enabled, standby offline, or absent. It also monitors the individual drive temperature, because a spinning hard drive generates significantly more friction and heat than a solid-state drive.
I want to focus on the difference between standby offline and absent, because, to a layperson, both of those terms just mean the drive isn't working. Why does the SEC make such a hard distinction?
Because they represent entirely different operational realities. Standby offline is a controlled software-driven state. The drive is physically sitting in the slot. It has power. The SAS controller, the serial attached SCSI controller managing the enclosure, can clearly see the drive's firmware.
But the SEC has simply told the drive to spin down its platters to save power, or perhaps it has removed the drive from an active storage pool during one of those composable infrastructure reallocations we talked about.
Exactly. It is asleep, but it is ready to be woken up via software at a moment's notice. Now consider absent.
Absent implies a physical void.
Absent means the hardware controller is screaming, "I am sending voltage down the pins to slot 4, and there is zero electrical resistance. Nothing is there."
So either a technician physically walked into the cold aisle, unlatched the caddy, and yanked the drive out of the chassis.
Or the backplane connector inside the server has catastrophically failed. It is a severe hardware event. If an administrator is looking at the dashboard and a drive goes to standby offline, they log it as a routine power-saving measure. But if a drive suddenly reports absent, and there was no scheduled maintenance ticket for a technician to be in that rack,
You have a massive problem. Either a vital piece of hardware just died, or someone is physically stealing your data.
the distinction between software state and physical presence is vital for security and uptime. But having petabytes of data sitting securely in a JBOF is useless if you can't actually move it to the CPU.
Which brings us to the macro traffic controllers of the entire system. The switches. The SCC monitors switch port counters, specifically tracking RX, which is receive rates, and TX, which is transmit rates. It also flags differential port counters.
If we go back to our composable infrastructure model, the switch is the central nervous system connecting the line cooks to the warehouse. A modern top-of-rack switch operates on what's called a cut-through architecture.
What does that mean?
It means it reads the destination address of an incoming Ethernet frame and starts transmitting it out the destination port before the entire packet has even finished arriving.
Wow. It's moving data at near the speed of light.
But that speed relies on perfect harmony. Let's look at a failure scenario using those RX and TX counters. Imagine a composed node is pulling a massive data set from a JBOF enclosure. The JBOF is blasting data out at 100 gigabits per second. The switch's RX counter of the data coming in from the storage shows it is receiving 100 gigabits perfectly.
Okay, so the switch is catching the ball.
But the TX counter, the port transmitting that data out to the CPU, is only registering 10 gigabits per second.
Where are the other 90 gigabits going?
They're being dropped.
Yeah.
Completely lost. The differential port counters in the SEC would instantly flag this massive discrepancy. The switch is receiving billions of packets, but failing to transmit them.
Why would that even happen?
It could be an optical transceiver, failing on the transmit port, degrading the laser signal. It could be a microscopic fracture in the fiber optic cable leading to the CPU rack. Or the switch's internal memory buffer might be overflowing because the receiving CPU is overwhelmed and sending pause frames back to the switch.
The switch is literally throwing the data on the floor because it can't push it through the pipe.
Exactly.
And without the SCC tracking both RX and TX simultaneously on a single pane of glass, an administrator might just see the CPU idling and assume the application crashed, completely missing the fact that the network switch is silently destroying the data in transit.
It really highlights the sheer interconnected fragility of the system. Every single component, the memory, the power supply efficiency, the thermal airflow, the switch buffers, they must all operate in perfect symphony.
But we know that eventually the music stops, hardware degrades, software panics. What happens when the system suffers a catastrophic, unrecoverable failure?
What happens when the plane crashes?
Exactly. How do administrators capture a snapshot of a failure to figure out what killed the machine? The manual outlines two specific autopsy tools, the dump feature and BMC events.
Let's examine the dump feature first. In IT forensics, live telemetry is useless after a crash because the system states are just gone. The dump feature allows an administrator to download a meticulously compressed zip file containing the entire state of the machine leading right up to the failure.
And the granularity of this feature is what really stood out to me. You don't just hit a panic button and download a 50 gigabyte file of the entire data center. You can target it. You can select specific data points, overview, system, compose node, power, thermal, or you can select a specific level of the hardware tree and dump data from all appliances within a single rack.
This is critical because of log rotation. Servers generate so much monitoring data that they constantly overwrite their own logs every few hours just to save storage space.
Oh, that makes sense.
Yeah, so when a catastrophic error occurs, the very first thing an engineer must do is freeze time. By targeting a specific rack and triggering a dump, you encapsulate the exact thermal states, the switch drop packets, the voltage fluctuations, and the memory errors into a static offline file.
It really is the black box flight recorder. You hand that zip file to the engineering team, and they can reverse engineer the timeline of the crash without touching the live production environment.
But that assumes the server's operating system was still functioning well enough to actually bundle and send that zip file. What happens if the server's motherboard physically shorts out, the CPU instantly halts, and the Linux operating system just vanishes in a microsecond?
The brain is completely dead. How does it report anything?
That is the domain of the DMC, the baseboard management controller.
The manual dedicates a specific section to compute details BMC event. It notes that the SCC tracks the event type, severity, message ID, message, and a timestamp down to the exact second. We need to do a deep dive on what a BMC actually is because it sounds like sci-fi.
It is arguably the most critical component on a modern server motherboard. A BMC is a highly specialized, completely independent microcontroller embedded directly onto the silicon of the board.
Independent meaning it doesn't rely on the main Intel or AMD processor.
Completely independent. It has its own dedicated low-power RM processor.
Yeah.
It has its own dedicated RAM. It runs its own embedded firmware. And most importantly, it has its own dedicated network interface port, physically wired to the back of the server.
Wait, really? So even if the main gigabit network adapters fail, the BMC can still talk to the network?
Yes. It operates entirely out of band. Its sole purpose in life is to monitor the physical hardware via an internal communication bus called I2C. The BMC is wired to dozens of microscopic sensors scattered across the motherboard.
Like what kind of sensors?
Well, it monitors the rotational speed of every single cooling fan. It monitors the exact voltage stepping down from the power supplies.
I read it even monitors chassis intrusion. It has a physical switch that knows if someone takes the lid off the server case.
Yes, the BMC registers the break in the physical circuit and instantly logs a critical security event. And here is the defining feature of the BMC. It runs on standby power. As long as the server is physically plugged into the wall, even if the server is powered off, the BMC is awake.
It is the immortal soul of the server.
It survives the death of the host. If a massive power surge hits the CPU and physically cracks the silicon, taking the main operating system down instantly, the SuperCloud Composer can't ask Linux what happened. Linux doesn't exist anymore.
But the SCC can send an API query directly to the BMC's dedicated network port.
And the BMC, sitting there calmly on its standby power, will respond with the event log. It will report at exactly 2026-06-15-14.32.01, voltage regulator module 3 exceeded operational limits, CPU 1 catastrophic thermal trip, system power halted.
It provides a certified death certificate with the exact message ID of the fatal error.
Without the BMC, an administrator would be staring at a completely inert block of metal, forced to guess which component failed through trial and error. With the BMC integrated into the SEC dashboard, they know exactly which field-replaceable unit to dispatch the technician with.
And tying this all the way back to the composable infrastructure we discussed in Segment 2. If a composed node fails, knowing the root cause via the BMC ensures the SEC software doesn't try to reuse those broken physical components when it allocates resources for the next workload. It just quarantines the bad hardware.
It is a closed-loop system of total observability.
We have covered an immense amount of technical ground today. I mean, we started by examining the human interface, looking at how an administrator can scroll a mouse wheel to flatten a histogram and peer through the quadrant magnification to find a millisecond of anomaly.
Right, and then we move down the hierarchy to the physical racks, unpacking how NVMe over TCP allows the SuperCloud Composer to act as a master chef, dynamically allocating and assembling raw compute and storage across the network fabric.
We analyze the intricate dance of system performance, realizing that aggregating memory bandwidth across NUMA boundaries is the only way to find the true bottlenecks starving our processors. We felt the unforgiving reality of thermodynamics, where a single missing blanking panel could trigger a localized thermal runaway via hot aisle recirculation.
We track the difference between a drive spinning down to save power versus a drive physically absent from the backplane, and how switch differential counters can expose a network quietly dropping gigabits of data. And finally, we explore the digital gravesite, where the immortal BMC logs the exact microsecond of a server's demise.
It is a profound level of control. The SuperCloud Composer provides an orchestration layer that takes the chaos of 10,000 disparate machines and unifies them into a single, understandable organism.
It does. But as we dissect this manual, a larger, almost philosophical question emerges about the future of this scale of technology.
Oh, what stands out to you?
Well, we have spent this entire deep dive marveling at how beautifully this interface is designed for humans. It utilizes intuitive quadrant magnifications, visually color-coded carousel views, and carefully categorized tree views. It is meticulously crafted to allow a human brain to read the telemetry, analyze the bottleneck, and click a button to fix it.
Right. It translates machine code into human intuition.
But consider the sheer velocity of the failures we just discussed. A switch drops 1 billion packets in the second. A composable node reallocates terabytes of NVMe storage across a TCP fabric in milliseconds. A thermal runaway event cascades from a hot inlet temperature to a physical hardware shutdown in under 3 minutes.
The machines are moving at the speed of light.
And we are moving at the speed of biology. If an alarm goes off at 3 a.m., by the time the human operator wakes up, opens the dashboard, sees the broken cloud icon, scrolls the mouse wheel to flatten the histogram, clicks the drill down report, queries the BMC for the event log, and deduces that the voltage regulator failed.
The damage is already done. The rack is offline. The human is too slow.
Exactly. At what point does the human operator sitting in that control room stop being the manager and start being the primary bottleneck? As these infrastructure environments continue to scale into the hundreds of thousands of nodes, and as telemetry generation moves from megabytes to terabytes per second, a visual user guide designed for human eyes becomes obsolete.
You are suggesting that the next iteration of something like the SuperCloud Composer won't have a dashboard at all.
I am suggesting that as these monitoring systems evolve from displaying predictive analytics into fully autonomous AI-driven management engines, the entire concept of a control room will vanish. The digital metropolis of 2030 won't wait for a human to magnify a quadrant. It will detect the microsecond latency spike, instantly rewrite the network fabric routing tables to bypass the failing switch, migrate the workload, and power down the degraded rack before a single alarm ever sounds. It will monitor, diagnose, and heal itself entirely in the dark.
Leaving the administrators entirely out of the loop. That is a staggering and honestly slightly unnerving reality to ponder as we look at these massive data centers powering our daily lives. The ultimate visibility might eventually require no eyes at all. Thanks for exploring the depths of this infrastructure with us. Until next time, keep diving deep.